Hello, this is Mrs. Sargent, and this is lesson 9.2, gas laws. So to start off with, in lesson 9.1, we discussed some variables that affect gases, and those included pressure, temperature, volume, and amount. Today we are going to focus on the first three variables: pressure, temperature, and volume. So there's some gas laws that we're going to use to determine what happens to these different variables. The first one is Boyle's law, and Boyle's law compares pressure and volume. And since we're only looking at pressure and volume, temperature and amount are held constant. So if you were in class when we made the PTV card, you can also use those for these laws as well. The equation for Boyle's law is P1 times V1 equals P2 times V2. So since we're holding temperature constant, you're going to put your finger over temperature, increase pressure, which is going to cause volume to decrease. Or if you decrease pressure, volume is going to increase. So since these are basically opposites of each other, they're not both increasing or both decreasing, this is what we call an indirect or an inverse relationship. So the graph is going to look like this, an inverse curve. Okay. So an example of Boyle's law is breathing. When you breathe, you have this muscle called the diaphragm. And when you inhale, this diaphragm muscle is going to go down, which is going to increase the overall volume of your lungs. And it is going to decrease the pressure. So you bring air in because air is always going to go from an area of high pressure to low pressure. When you exhale, your diaphragm muscle is going up, and so the volume of your lungs is going to decrease, which is going to increase the pressure of the gas in your lungs. And this forces air out because, again, air is going to move, or gases in general move from an area of high pressure to low pressure. Think about just, you would rather have some elbow room than being crowded shoulder to shoulder next to someone. That's the same type of thing that our gas molecules want. They want some room to move more freely. So this example problem for Boyle's law, it says a high altitude balloon contains 30 liters of helium gas at 103 kilopascals. What is the volume when the balloon rises to an altitude where the pressure is only 25 kilopascals? So as I read through this question, I underlined the number of units that were given to me, and I circled the unit that I wanted to find, or the variable I wanted to find. So 30 liters, this is going to be our V1. 103 kilopascals is going to be our P1. We want to find V2, and we are given P2. So our equation for Boyle's law, P1 times V1 equals P2 times V2. So now we're just going to plug in the numbers into our equation. So 103 kilopascals is P1, 30 liters is V1. We want to find V2, so our P2 is going to be 25 kilopascals. So then we just need to divide both sides by 25 kilopascals to get V2 by itself. Pascals is going to cancel. So V2 equals 103 times 30 divided by 25. And I got 124 liters when I did my calculation. I rounded to 3 sig figs because I was given 3 sig figs throughout the problem. In our next law, Charles' law, it compares volume and temperature. So pressure and amount are held constant. Our equation is V1 divided by T1 equals V2 divided by T2. So if temperature increases, and again, you can use your PTV card, and this is a good way of just checking to make sure your answer is along the right lines is by using your PTV card. So we're holding pressure constant, so we're going to put our finger over that. As temperature increases, volume is also going to increase. And if we did it the other way, so temperature decreases, volume is also going to decrease. So since these variables are both going in the same direction, this is going to be a direct relationship. And so your graph is just going to be a diagonal line going out from the origin. As temperature increases, volume is also increasing. Volume increases, temperature increases. So an example of Charles's law is a hot air balloon. So inside a hot air balloon, you have your gas, and what we have is we have a fire that is going to increase the temperature. As we increase the temperature, the gas molecules are going to want to get away from each other, which is going to increase the volume. It's a flexible container, so it's going to increase the volume of that balloon. It's the same amount of air, though. That is important. Same amount of air or gas. So it's just causing the volume of that amount of air to increase. And if you remember back from the beginning of the year when we used our density equation, density equals mass divided by volume. So our volume is going to increase, which is going to decrease our density. So since the density is decreasing, what's wrong? There we go. That is going to cause the balloon to float. Think about just a less dense object and a denser object in water, the less dense object is going to float, and the denser object is going to sink or not float at as high a level. So same is true with the hot air balloon. The gas inside that balloon is less dense than the gas around it, and so in that case, the balloon is going to float. Charles's law example problem here. A balloon is inflated in a room at a temperature of 24 degrees Celsius and a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees Celsius. We want to determine what the new volume of the balloon is. So here's T1, 24 degrees. V1 is 4 liters. T2 is 58 degrees Celsius, and volume 2 is what we're solving for. Now, these temperatures are in degrees Celsius, so we need to convert those to Kelvin. So you're going to add 273 to your degrees Celsius. Okay, so we have 297 Kelvin and 331 Kelvin. In Charles's law, V1 over T1 equals V2 over T2. So now we can just plug in our the values into our variables in our equation. So we're going to have 4 liters divided by 297 Kelvin equals V2, which is what we're solving for, and 331 Kelvin. So this is going to be, we need to do some cross multiplication. 4 liters times 331 Kelvin equals 297 Kelvin times V2. So then we're going to divide by 297 Kelvin on both sides to get V2 by itself. Kelvin's going to cancel over here. So we're going to have 4 times 331 and then divide it by 297. So V2 is going to equal 4.46 liters. Now, if you were to take a look at your PTV card, and we're holding pressure constant, let's just take a look back up here at our problem. So we know that our temperature is going to increase, so that our volume should also increase. So let's take a look at our answer. Did our volume increase? Yes, it went from 4 liters to 4.46 liters. So it increased. It didn't increase by a ton, but it did increase. And that's just a way of checking your gas law problems to make sure that your answers make sense. Our next law is Gay-Lussac's law. Gay-Lussac's law compares pressure and temperature. So that means that volume and amount are held constant. The equation is P1 divided by T1 equals P2 divided by T2. So again, if you take a look at your PTV card, we are holding volume constant, so put your finger over that. if you increase the temperature, your pressure is also going to increase. Or we can also decrease, which is going to decrease both of them. So again, this is going to be a direct relationship because the variables are moving in the exact same way. So your graph is going to be a diagonal line going out from the origin. So an example of Lussac's law is popping popcorn. When you put your popcorn in the microwave, you are increasing the temperature, which we know from Lussac's law means that the pressure should also increase. So what's happening to cause your popcorn to pop? Inside the kernel of corn, there's a little bit of water. As the temperature increases, the water goes from a liquid state to a gas state in the form of steam. But this kernel is not really that strong, the shell in the kernel. And so once the steam, it's in the gaseous form now, so pressure is going to be increasing, and it's going to eventually cause that kernel shell to pop off and then allow the popcorn to form. So that's how popcorn is made, for instance, in your microwave. We're going to take a look at an example problem for Lussac's law. A gas has a pressure of 6.58 atm at 539 Kelvin. What will the pressure be if the temperature decreases to 211 Kelvin? So this problem, our temperature is already in Kelvin, so we don't have to do any temperature conversions. P1 is going to be that 6.58 atm. T1 is going to be 539 Kelvin. P2 is what we're going to solve for, and T2 is going to be 211 Kelvin. So our equation, P1 divided by T1 equals P2 divided by T2. So now we're just going to plug in the values. So again, do some cross multiplication. So we're going to have 6.58 atm times 211 Kelvin equals 539 Kelvin times P2. Divide both sides by 539 Kelvin. Kelvin's going to cancel. So we're going to take 6.58 times 211 divided by 539 to determine our second pressure, which should end up being 2.58 atm. And those are the three gas laws that we talked about. If you missed class, be sure to ask me about getting your foldable paper for your gas law equations. That will just help keep all of the different formulas or equations that we're talking about throughout this unit together when you're working on your practice and homework problems. If you have any questions, feel free to stop by and ask questions. Thanks for stopping by, watching the video. Have a great day.